Good evening, everyone. My name is Harry Helling. I'm the Executive Director here at the Birch Aquarium at Scripps. It's my great pleasure this evening to introduce our speaker, Dr. Helen Amanda Fricker. Helen is a glaciologist and professor here at Scripps Institution of Oceanography, University of California, San Diego. She's a native of England. She received her Bachelor's of Science in Mathematics and Physics from the University College in London, and her PhD in glaciology from the Institute of Antarctic and Southern Ocean Studies at the University of Tasmania in Australia. In 1999, she began her work here at Scripps, a postgraduate researcher. Now 20 years later, she's a professor in geophysics in the Cecil H. and Ida M. Green Institute of Geophysics and Planetary Physics, lovingly known as IGPP here at Scripps. Helen is an expert in the Earth's cryosphere, that's the frozen water part of the Earth system. Using a combination of satellites and remote sensing, Helen conducts research on the ice sheets in Antarctica and Greenland to better understand their impacts on the climate system. Widely recognized for her discovery of the active subglacial lakes, she was the first to describe Lake Wellens, an active subglacial lake in the West Antarctica, which was subsequently the first such environment to be sampled and found to contain life. She was also one of the primary investigators in the first group to drill into an Antarctic subglacial lake in 2013. And tonight you'll be some of the first to see her recent data, for just days old, and we're all excited to see that unveiled as part of her talk this evening. Helen is not only a distinguished researcher, but also has played an important leadership role in advancing the science of the cryosphere. She's held numerous leadership positions, including serving as chair of the American Geophysical Union's Cryospheric Sciences Focus Group and as member of NASA's Ice Cloud and Land Elevation Mission Science Team, the ISAT Science Definition Team, and the NASA Sea Level Change Team. She runs the Scripps Glaciology Group and is the co-director of the new Polar Science Center here at Scripps. Among her most recent and of many accolades, Helen was awarded the Martha T. Muse Prize for Science and Policy in Antarctica by the Tinker Foundation in 2010 and was elected as Fellow of the American Geophysical Union in 2017. We are delighted to have Helen here this evening and for her talk entitled Lakes Beneath Antarctic Ice, Deep, Dark, and Mysterious. Please welcome Helen Fricker.
Thanks, Harry. Thank you for that very nice introduction, Harry. We even have stickers for the Polar Center now. Grab one on your way out. How many did you make? Not very many, but the first few of you can get them, so it must be a real thing. Okay, so I'm going to take you on an adventure underneath the bottom of an ice sheet. But first of all, I want to give you some background as to why we went to this particular place and just to give you some idea of what we were expecting to find. This photograph was taken not very many days ago in Antarctica, and this is looking down through a borehole drilled through the Wellens ice stream and Mercer ice stream over subglacial Lake Mercer. So I'm going to talk about the discovery of the lakes, how we managed to find them, sitting here in La Jolla. Antarctica is a very long way from here, but it does actually impact all of us. And you can actually study it by being here. So we're very lucky to be able to study Antarctica from beautiful climate, although tonight you might argue that it's not so beautiful. And thank you all for coming here, even though you probably all had to traipse through rain and whatnot to get here. Okay, so this is just going to give a little bit of context onto ice sheets and sea level, what they are, what we study. So there's two ice sheets on Earth at the moment, or in the present day, Antarctica and Greenland. I mainly study Antarctica, and this is what this talk is all about. So you may have heard about the melting ice sheets and the melting ice caps. People refer to them sometimes, but ice sheets is the correct name. What happens when the ice melts from Antarctica is it will actually end up in the ocean if you have extra melting going. So essentially what's happening on an ice sheet is you're getting snow falling in a very cold place. It doesn't melt enough at the end of the summer to go away, so it stays there. It becomes layers upon layer over hundreds and thousands of years, and we're accumulating these very large stacks of ice over a continent. So the difference between the amount of ice that's added onto the ice sheet and the amount of ice that's lost around the edges in these very interesting regions called ice shelves gives us a balance. And if we're losing more, so the more of the red terms coming away than the green terms being added by snow accumulation, then we will have a net mass loss, and that ice will go into the ocean. My group is very focused on these ice shelves. They're very interesting because they're kind of where the rubber hits the road for an ice sheet. This is where the ocean is coming in underneath and melting. And we are very interested in what's causing that to happen. So ice shelves are very important because they're actually pushing back on the grounded ice behind them. So if you reduce the amount of mass that's in an ice shelf, you will remove the restraint of that grounded ice, and you will actually release more grounded ice to the ocean, and that will affect sea level. That's why we're very interested in that, especially even here in La Jolla, we will feel the impacts of sea level rise from the ice sheets all around the world. This is quite different to melting sea ice, and the problem that many people are looking at is changing sea ice, especially up in the Arctic. That's also very important for climate, but it has a different impact. It doesn't affect sea level because it's already displacing its weight in water. Okay, so the sea level potential of Antarctica is very large. This is a nice plot that my postdoc Cyril, who's here, put together, showing us the basins and the actual sea level equivalent in all of these basins. This is in meters, so multiply that by 3 to get feet. All of Antarctica and Greenland, all added up together, is something like 180 feet of sea level. So this is a lot. So how do we monitor these very large masses of ice? This is a very vast continent, impossible really to get a good measurement just by going in boots on the ground because it's so huge, you can't really make a dent in that. So we have to put satellites up, and for the last 20 years or so, we've had a really nice sequence of satellite instruments from the European Space Agency and NASA, and I've worked with a lot of these instruments to collect a time series to understand how the ice shelves and the grounded ice are changing. So we get a long time series so we can actually understand what we're seeing in the present day. Ice shelves are floating on the ocean. This is important for what I'm going to tell you for how I discovered the lakes. So this is just a very, very crude schematic of the Ross Ice Shelf over a 24-hour tidal cycle. So you can see the whole thing is coming up and down, oscillating with the tides. This is an ice shelf the size of, well, if you're from Europe, it's the size of France or Spain, approximately. And here in the US, the analogy is Texas. So this is about the size of this ice shelf. It's vast, it's massive, it's going up and down, pumping going up and down with the ocean tides. And what that does is it means that the height of the ice is different at different times in the tidal cycle. So we actually chose to exploit that when we were looking with this mission called ICESat. And what this is on the right, I don't show many graphs in this talk. Cheryl asked me not to, but this is one because it's kind of important. Well, I know I didn't want to kind of show too many equations at this time of night. But this is an important one, and so bear with me for a minute. So the top here is a profile going across, going from the grounded ice to the ice shelf at different times. So this is 4 different times, and each time the ice was at a different height with respect to the tide. So high tide, the signal is going to be higher than at low tide when it's lower. So you can difference those, and you can pull out what's happening over the ice shelf. And we're seeing about 5 or something meters of elevation change. So about 15 feet of rising and falling of the tide in the tidal cycle. So we use this technique to go all around the edge of Antarctica to map out this point right here. So this point right here is a point that we wanted to map, because this is a point where above it or upstream of it, you have grounded ice, and downstream on the ocean, you have floating ice. So we want to actually map that all around Antarctica, which is what we did. So back in May 2006, there I was sitting at my computer down the hill here. My office used to be just at the bottom of the road that leads up to the aquarium. And I was literally sitting there looking at the Whillans ice stream. I can't actually remember why I was looking at the Whillans and the Cycle Coast. I'd never actually studied this region before, but it's somewhere that I knew that we really needed a good grounding line. So this is a grounding line that we thought it was at the time. This is before we did any of this mapping. This black line is where the grounding line is. So the grounding line is where the ice lifts off the bedrock and starts floating. So this is a sensitive point we're trying to map all around the ice shelf perimeter. So this is floating ice here and grounded ice here. So we did that, and this is what the tracks look like, the ICESat tracks. So this satellite was up between 2003 and 2009. And these are the repeats along the orbit, or on the ground tracks. The different colors just mean different elevations. The details don't really matter. The point is that I decided to look at this track. And it's probably about the first or second track that I looked at in this system. And the point is that it went across the grounding line here and then it went up here. See how there's a region in here that looks a little bit different? The elevation's a little bit lower, the colors are lighter. So what happened was I pulled out and I plotted these profiles, all the repeat profiles along this line, and this is what I saw. Okay, so right here, you can't quite see, but this is about 5 meters per year of signal. It's about 10 meters or 30 feet of drawdown of elevation upstream of the grounding line. So the grounding line was about here, really noisy actually. Turned out this is a horrible track for mapping the grounding line. But what we found was this ribbon of colors going down in order from, this is early through to later, a few months later. And what had happened was the surface of the ice had gone down by about 5 meters over that time. This is one of those aha moments that I'm probably never gonna have ever again. I think I've heard that scientists can have these a couple of times in their career. This was kind of amazing. This happened on a Thursday at the end of May 2006, right before Memorial Day. And there I was going, oh, okay, I think I might have stumbled across something really big here. And then, of course, the next thing to do was to look at the tracks that go across, and everybody that I kind of shared this with, it wasn't many people, were like, maybe there's a problem with your data. It must be something wrong with your data. Of course, couldn't possibly have found a whole new phenomenon. Well, turned out we had found a whole new phenomenon, but off I went to Catalina for the weekend. So I was sitting on this gold mine of discovery, and my 2 daughters that are in this picture, Zoe and Millie, were only about 3.5 and 1.5 at the time, and off we went. We lived on our boat here. This is our old boat Karma, and off we went to Catalina, like you do when you are a young family living on a boat. And I had to leave all of this behind. It was kind of amazing. I mean, this is before we had phones and everything, so I literally could not look at this stuff for about another 5 days, and it was kind of killing me. We had a fantastic time, but it was like, what have I just found? This is me at my desk before I left. Actually, I think it might have been recreated because they came and took a photo afterwards. I mean, it's really not very interesting photographing what we do, sitting looking at data, so that was about as good as it got, you know, sitting there. Right, so there we have it. We found this whole system of lakes, and I then knew, wow, okay, so I'm going to have to do something with this. This is a really big discovery. It's actually changing our whole picture of what the subglacial system looks like in Antarctica. We did this technique called image differencing. One of the things about ICESat, that it's a great satellite in terms of a long track resolution and spatial resolution, but you can see that the tracks are quite wide spaced. So this is it's about 3 or 4 kilometers from that point to that point. So if you're only mapping there and then there and then there, you really don't have a very good picture of what's going on. So the image differencing technique really brought out that beautiful spatial context of what happens. So you can actually see, most of you will probably see this, depending on if you're looking at it upside down, it's either coming out at you or going in. It's one of those weird pictures. But people said it looked a bit like a giant's footprint or the Yeti. So this was subglacial Lake Engelhart. Turned out to be just up from the grounding line. The grounding line's right here. This is only a few, like 10 kilometers or so. It's a really beautiful lake. We've not been there. No one's been there yet. NSF actually told us it was too dangerous to go there because it's very near the shear margin here, and there's lots of crevasses and things, so they don't want people to be conducting fieldwork in really dangerous places. So we have so far not been able to go in there. I'm sure one day we'll find a way to get there. But what we did do was we teamed up with a colleague, Slavek Tulichik at UCSC, California, Santa Cruz, and he had just got funded to put GPS on lakes. Now, the lakes that he had just been funded to put GPS on were not these lakes, because we hadn't discovered these yet. But he heard about these lakes, and he said, he called me up one day and he said, how do you feel about us going and collaborating, and we'll put instruments on your lakes? And I thought, well, that's just fantastic. Within 6 months of discovering these lakes, we had GPS on the lakes that were helping us to monitor what was going on. We had a GPS on each lake apart from the fantastic one, but all of these, to not only look at what was going on in terms of the activity of the lake, the rises and the falling, but also whether it's affecting the ice dynamics. Because once the lake floods and the water goes from the lake into the subglacial system, the theory is that we should see some changes in dynamics. So that was what the GPS deployment was all about. So that was the history of the exploring these lakes on the ground came from. So these lakes, is about 14 of them in this system, and turns out they're all connected in different ways, in 3 different systems. So back in 2006, this is the picture that we had right before that. This is a colleague of mine in the UK, Martin Siegert, and this is an inventory that he had published just the year before. And this is where he said all the lakes were. So you can see that my lakes weren't on there. He didn't know about those. These lakes were only ones that were near the ice divides that had been found by people flying over with aircraft and using ice-penetrating radar to go through the ice and finding water at the bottom. This is how they found lakes before. People didn't think that lakes did this activity thing where they rise and fall. That was just not part of our understanding. So my discovery actually wasn't, there were 3 papers at the same time that came out, sort of 3 years in a row in different parts of Antarctica that all, when taken together, gave us a new picture of the subglacial system. So this is the first study, which is really just to show you what is going on at this place. So this is in the Adventure Trench, there was another survey. This is a UK authors, Duncan Wingham et al. And they were looking at altimetry just at one spot on a lake. And at one place on a lake, the time series went, the elevation drew down by about 4 meters or so. And just downstream of it, it rose by a meter or so. But also there was another one downstream. So added together, all these lakes were part of a system where there was 1 lake draining and 3 lakes receiving all of the water. And this is a cartoon explaining what's going on here. So this one actually only has 2 lakes rather than 3, but this is the upstream lake, and the lake water is leaving, going down. The surface is responding. This is the key thing about this technique, is that the altimeter is detecting the surface of the ice, which is responding to what's going on at the base. So the water is leaving the lake cavity, and it's no longer holding up the ice, so the ice falls down. And that's what you're detecting on the surface. This was kind of transformational because we realized, wow, we can actually use remote sensing to map the ice, what's going on with these water systems. And it's not that surprising that we have subglacial water under Antarctica. We did know about this, but the fact that they're so active was the key thing that was quite different only 12 years ago or so that we discovered. So this is a movie that the NASA Visualization Center put together to help explain what we're seeing here with the altimetry. Okay. So this is starting at the top, coming down through, cut away. Now the upstream lake is the one on the left, the downstream lake is the one on the right, and you'll see that the water goes from the upstream lake to the downstream lake, and you see that the ice surface has responded at the same time. So that's what we then, looking back, this fades into the data on the left, more or less. It's a little bit different because we use different color schemes, but this lake is this one, and this one is this one. So this is what we're seeing, and this is what we're detecting with the altimetry. This was only with a few months of data. We only had at this time, about 3 or 4 years worth of data. So every time we got a new sort of observation from ISAT, we could increase our knowledge of what was happening, because it turns out these lakes are actually changing on sort of annual, multi-annual, subdecadal timescales anyway, kind of changing on about the order of between 5 and 10 years or something like that. So they're filling up, they're draining. They're filling up, they're draining. And we're using the satellites to help us understand and the GPS to tie it all together. One thing that we found by looking for a little bit longer was that there's actually connectivity between lakes, where this lake here, which is up against this ridge here, Conway Ridge, when it drains, all of its water goes into this lake here. So this is really nice because we're seeing this hydrological connection where one lake is draining into the other one. Okay, so then there was an inventory that was created. My colleague Ben Smith actually took the lead on this, but we joined forces and we looked over the whole of Antarctica, all of the ISAT tracks over Antarctica, and pulled out where we could see signals like this. And we found 124 lakes in this way. And you can see they're all over Antarctica, and they're all the way down in the ice streams where the ice is moving fast, and they're down near the grounding line. And once the water leaves the lake across the grounding line, it then enters the ocean. And that's a key thing as well, because now we know that subglacial water it has entry points into the ocean from underneath the ice sheet, which is a very interesting thing for sampling and planning and trying to see how that might affect the circulation of the ocean as well. So this new picture that we got from all of this work, these 3 papers, including mine, helped us understand. So this is I showed this before, but I didn't really explain what it was. So this is a NSF program. There was an artist for NSF who did this, and she basically showed the rivers and the streams that are connecting the active subglacial lakes underneath the ice sheet. So just lift all of the ice up, and this is what you see underneath. It's very difficult to get to this place. The average thickness of Antarctica is about 2 kilometers, so very, very challenging to make measurements down there. That was why this realization that you can detect from the surface was so transformational, because any information you can gather in that way is really helpful. Okay, so after we put GPS on all the lakes to monitor them, we then started to put together proposals to go down there and start drilling. This is the next thing. We want to go down there and drill. Now, drilling is we often have negative connotations for drilling. Drilling in this sense it's an exploration. We're going in to find out what's at the base of the lake, what's under the ice sheet, what's in the lake, like what is actually happening at the lake floor. Can the sediments tell us anything about the history of how often these lakes have drained and filled in the past? How long have they been there for? We don't know that. We really don't know anything about these systems. It's such a new field. So this project, the first project that we started to work on was called WIZARD. So this is the top one. WIZARD is an acronym that I did not come up with. It's Willan's Ice Stream Subglacial Axis Research Drilling. So this is to go drill to the base of, they wanted to drill into 2 lakes, but we got cut in half, and then we got cut in half again. So we ended up drilling into Subglacial Lake Willan's. SLW is Subglacial Lake Willan's. It's on Willan's ice stream, so that's why it was called Lake Willan's. And then we got to drill downstream, and this dotted line here is where the water goes when it exits the lake and travels underneath the ice sheet to the ice edge, crosses the grounding line right here. So back to my grounding line that I was trying to map. Kind of didn't get very far with that bit. Passed that on to someone else. We got a bit distracted. So we were drilling right here at the grounding line and here at the lake. It was one long hydrologic continuum. And turns out this was a really nice project. We got lots of very nice data from this. They actually got into the lake at the beginning of January 2013. And they found it was an interdisciplinary project involving biologists and glaciologists and oceanographers. And we were able to uncover a whole new microbial ecosystem that had not been discovered before under the ice sheet. So this is the diversity of the cells that was found. This paper's in Nature, and this is a team of all of us, the WIZARD science team. I'm included in that. So don't ask me any more about this. If you want to know about this, we can link you up to the authors, my wonderful colleagues that know all about this. I mentioned the link between lakes and ice dynamics. As lakes drain, the water will perturb the subglacial system, and it's just like if you have water on the floor, you might fall over, just like out there, be careful. You also can do that by if you have water under an ice sheet, you can actually reduce the friction and the ice will flow faster. And we've only seen this in a couple of places. And one of those places is Bird Glacier, where 2 lakes drained for a period of about 14 months, and we did see an increase in the ice flow velocity that lasted to coincide with that time. There isn't very much coincidental velocity data and elevation data, so we're definitely, it's an active area of research to try and find these links. So then ISAT stopped working in 2008. Or 2009. So what do we do after that? We're kind of in the dark. We've got this blind spot. We don't know what's going on. There is another satellite that was launched after ISAT called Cryosat-2. And it's a European mission. It's a radar, slightly different to the laser technique that we used on ISAT. And then there's an ISAT follow-on mission called ISAT-2, which has just launched, which I'll show you. So we did obviously want to find out what was happening with our lakes all around Antarctica, so we mapped with Cryosat-2 all the lakes that we had found with the original technique with ISAT, and we went in and managed to extend that, so we have been able to do that. It wasn't the best because not all of the lakes had good enough data to do it. But ISAT-2 is going to be hopefully the answer to all of our questions in terms of what's going on with these lakes. We can monitor them for longer. We just launched this satellite in September. We were all at the launch. We saw it go up. We all, as in me and my family, my kids, we went and saw this thing. We got up at 5 a.m. and saw it launching from a golf course near Vandenberg Air Force Base. It was really exciting. It's been delivering data now for a couple of months. Unfortunately, there's a shutdown at the moment. And so the project is kind of a little bit in limbo, but we are all still working pretty hard. We are getting data through channels, and we're doing things, but it's definitely impacted by the shutdown because all the people who are project scientists for the mission are not able to come to work. But there is a lot of data, so the launch was very exciting to watch. The data is transformational in what it's delivering. We're getting very, very good spatial resolution. For every ISAT point, you have 6 ISAT-2 points because the beam is actually split into 6. So it means the along track cover it, and the across track is very, very good for giving us slopes, which is what we need to understand lakes and ice sheet elevation. This is an artist's impression of the launch, which I really loved. This is the artist here. She also did sketches of me and my colleague Laurie Magruder, who is the science team lead. We did a NASA TV thing. So this is a really nice website to go and visit. The ice sheet elevations that have been delivered from ISAT-2 are already looking really promising. And what we are now hoping to do is go in fine detail once we've got the data all calibrated to really understand how these lakes have have been behaving over the mission life, which has only been a few months so far. This is a picture that I wanted to show because actually it's really lovely because it's showing us what we had always known we could do with ISAT-2. This is the front of an ice shelf. And right at the front of an ice shelf, you get this very interesting effect. It's my student Maya Becker has looked at this, and she made this plot for me. And this is three parallel beams. And what we see is this, it's called a rampart and moat feature at the front, and this helps us understand what's going on with the melting right at the front. Just an example of how much information we can get from ISAT-2. And then basal channels, we're getting information as well. This is Cecile put this together, and this is showing you what we can do, and then we know that this is the kind of technique we need to monitor those lakes. So we're very, very confident. There was a ISAT-2 pass over the lake, this lake here that they're drilling now, at the end of, it was 26th of December. We haven't seen the data yet, but once we see it, we should know what exactly ISAT-2 thinks that lake height is. So SALSA is another acronym that I did not come up with. this is the logo for that project. So this project followed on from Wizard very nicely, and the main thing being that the location of the lake that they drilled changed. So Wizard was focused on subglacial Lake Whillans, and Salsa moved over to subglacial Lake Mercer. One of the things that happened when we drilled into Lake Whillans was we got there and we drilled all the way to the bottom, and there'd been an estimate of how deep the water column was going to be from the radar. So this is the same technique that we used for mapping lakes in the first place, and it estimated that the water column would be on the order of 5 to 8 meters. So they go in there and they drill and they get to the bottom, and the ice column was only 1.6 meters. So this is about an order of magnitude lower than we were hoping, or about 5 times lower than what we thought. And it's not much water to sample, so people were a bit disappointed. The biologists were disappointed. So the paper that we got was great, but they were hoping for more, and they were hoping for a deeper water column. And I'm happy to report that they penetrated this lake in, actually the same day ISAT-2 went over it, December 26th, and they found a 15-meter water column at the right under. So the height of the water column at the base of the Mercer ice stream under subglacial Lake Mercer is 15 meters, which is really nice. This is a huge amount of water for them to sample and take measurements of to find out what's going on there, pull out sediments, and understand the history. Okay, so this is them arriving at McMurdo. A lot of this, all of this field work is governed. Insightful Coast has to go through McMurdo. They fly down to Christchurch, and then go by C-130 from Christchurch to McMurdo. And many people in the audience have been on this treacherous adventure. I actually haven't been able to go to Antarctica by this method before. I went by ship many years ago. But this is a really common way to do field work down there. And it's all done in the summer months, so that's why it's just been completed, because the summer in Antarctica is right now when we're in the winter. So they're all just coming back and reporting, and actually a lot of the photos that I'm about to show you have literally just been taken and sent all the way from Antarctica. This is showing a experiment that was done right before the drilling. I mentioned that the radar estimate of the water column wasn't as accurate as we'd hoped. We're hoping that this new technique, which is EM, this is a similar, same technique that they used to look for oil and gas. This is a former faculty member from here at Scripps, Kerry Key, and he and Matt Siegfried, who was my student and then postdoc, and now he's moved on, but he still works with us on these projects, leading all the geophysics. So they've been down there, and Chloe Gustafson, who was a graduate student here, is now at Lamont as a grad student, and the three of them have been down there while we've all been enjoying the holidays and everything. They've all been doing this, and they're actually still there. Chloe and Matt are still there on the ice stream. They left in October, and they're still there. And so the data that they're going to collect are hopefully going to be really valuable for understanding these water systems. I want to show you the EM setup that Kerry sent me. This is a little time lapse of what they do to set up one of these stations on the ice, which is measuring and hopefully getting us an idea of what the water column thickness is. So this is just a time lapse showing them going in and setting this thing up. You can see the clouds moving, so you can see time's passing, and in they go. And so every time they put out a station, they have to go through this. It's pretty hard work. And this is not La Jolla. This is cold. If you've ever been to the top of Mammoth, you know how cold it can get. This is even colder. So they've been there, and I think they're ready to come home by now. Matt's kind of a bit over it, I think. Okay, so after Matt and Chloe and Kerry, and also we had a mountaineer with them, 4 of them, after they completed their work, the Salsa Traverse had arrived. So this is a very large project. We've been planning this project for about 2 or 3 years now. I actually wish I could remember the exact dollar amount that's been spent on Salsa now. It's something in the order of $10 to $12 million. It's a big project, many people involved, I want to sort of convey to you the scale of the infrastructure that's required to undertake a project like this. You're drilling through 1,000 meters of ice. This is not, you don't just go out there with your screw from Home Depot, you drill from Home Depot. You actually have to really, really like plan this out. And they need to also use hot water drilling that has very clean access. Like the protocols are incredibly high for clean access, but they can't contaminate the subglacial water system. So everything has to be very, very well and planned out. This is a very nice 360 panorama that Tristy, one of the graduate students on this project, posted of the camp. This is when you have lots and lots of people in Antarctica all working on a project for several weeks, they basically make their own little city. So this is they call this tent city. So this is where like different people sleep in all these different tents, and there's a big food tent. And I mean, this is a massive operation. I love this one. This is taken with a drone. This is the entire team right after the project ended. I think this was taken it was probably taken about 4 or 5 days ago with a drone. So you can see the tents there again that I just showed you in the whole camp, the drill system. Just a bit of a, now, Matt is, help me out guys, Matt's there. I think Chloe's there. Is that Chloe? It is, right? Who else do we know in this picture? Oh, the cactus, yeah. Well, I told you they're missing home, so they're feeling a bit cold at this point. And this is the drill, which was somewhere in the background in this one. I believe it's in here. So this is the crane, and then lower, and this is the platform that they all hover around when they're working. The borehole actually penetrated the lake at the end of the day on, I call it Boxing Day, 26th of December. And then it actually stayed open for about until the 7th of January, so however long that is. Those days all blur into one. I think about 10 days it was open, and they did multiple, it was like being on a ship where you have watches. They had watches, people coming in, and someone's in charge, and then people are making measurements, and all different instruments go down the borehole. They have to keep the borehole open because it all just wants to freeze again because it's so cold. It's a huge operation. This is not quite right. This actually was the figure that was done for Lake Whillans. This is actually deeper. Lake Mercer was just over 3,000 feet. There was some press on this. It came out over the Christmas New Year break, so many of you may have missed it. I can share links with anyone that's interested. There was a story in Nature, another story in The Earther or Gizmodo by Maddie Stone. She's done some really wonderful media on this. So this is the cover photo from my talk. This is just a closer looking up at the drill hole around the edges. This is what they do to collect the core. So the coring element goes down right to the bed, all the way through the water, and then down to the bed into the sediment, and it'll actually pull out sediment. I think they got a core that was something on the order of 12 feet or something. I need to remember those numbers. I literally found out a lot of this stuff this afternoon before I came up here from Matt, who is sending me emails from Antarctica via Iridium. So this is how new all this stuff is. Now this is very new, and this is, no, I don't think a public audience has seen this yet. This is a video from the bottom of the lake. So just imagine we're at the base of subglacial Lake Mercer. It's just over 1,000 meters deep, and they have, for the first time, put a camera down there. And what's at the bottom? Don't worry, it's not a big surprise. There's no lake. There's no gremlins or anything. So there we are. We're right at the base of that. I know it's very, very short, but that was it. Yeah. So this is kind of amazing to think about the environment that they're in, that they're working in, the amount of effort that went in to get them there. Oh, we can cycle this. And you get to the bottom, take a sample of the lake, find out hopefully how long it's been there for, if we can understand how these lake systems fit into our understanding of the ice sheet in the context. One thing that's really important to know or remember about lakes like this is they're not something that's going to change with climate change, because they're very, very deep and they're not affected by changes on the surface. Like the bottom of this part of Antarctica doesn't know anything about what's going on the surface. So it's not a climate-related signal. But what it is that's interesting, the fact that it was a new discovery only a decade or so ago, it's kind of cool because it makes you think, well, how many more things are there to discover about the planet that we just don't know? So yeah, if you're interested in following up more about SALSA and this lake project in particular, there's multiple ways you can do that. This is the SALSA Antarctica website right here. They post a lot of this stuff on a field blog, so you can get a lot of that. They're all at McMurdo now. Some of them are sort of coming back to the US in the next couple of days. And then one of the best ways to follow many of us is through Twitter. I'm on Twitter, Scripps Glaciology is on Twitter. We've just started this Polar Center, which I'm about to tell you about, here at Scripps. So the Scripps Polar Center brings together many polar scientists across Scripps. Turns out there's many of us that already do polar science at Scripps, but we've never really labeled ourselves as a polar research institution, but this is hopefully going to change that. So Fiamma Stranio and I are the co-leads of this new center, and it combines and spans the Earth section, the Oceans and Atmosphere section, the biology section at Scripps. Beautiful logo was made by Jennifer Matthews, who's our graphic artist in IGPP. This is where we're situated in Maison. We don't have this whole building. We have this wing of this building, but maybe one day. And here's our lovely view. These will be eventually replaced with pictures of ice. So yeah, come visit us. And this will be our website. It actually doesn't have any content there yet, but it will. This is all kind of a work in progress. I was told that there might be some people in the audience that might be interested in how I got into polar science. So I'm going to take you back to me in 1990. So I went to UCL in London, did maths and physics, and it was all kind of interesting and everything, but it wasn't really that interesting. It was okay. But then I met this guy called Chris Rapley, and he was teaching this class called Physics of the Earth. And he really kind of changed everything that I studied, because suddenly that was it. I could understand why everything that I'd learned, why it mattered. And it matters because it helps us understand the Earth, and geophysics to me was what I wanted to do. And I remember going to talk to I've told Chris this story several times. We laugh about it. He comes to AGU quite often now. He's a climate science communicator now at UCL. And the other professors in the department weren't quite so, they thought Chris was a bit crazy. They said, oh, he wants to map the world's oceans with satellites. And this is back in 1990. They hadn't even launched ERS-1 yet. And I sat there and said, yeah, and that sounds really great. I'd love to do that. So anyway, long story short, I ended up doing a project with him and was able to then get a research position in Australia. And I got a scholarship from the Britain-Australia Society as an overseas student in Australia. And I worked in Tasmania, in Hobart, at IASOS, as Harry said at the beginning. That department actually doesn't exist anymore. It's gone. It's called IMAS now, Institute of Marine and Antarctic Studies. It's very nice on the waterfront in Hobart. I went to Antarctica. That is me on the Amory Ice Shelf. That was a long time ago now, though. And I came to Scripps nearly 20 years ago to work with Bernard, who some of you will know, on NASA's ICESat mission. And so ICESat-2 is just the next step of that. I'm on the science team. I just wanted to say one last thing about AGU and honors, and I showed this at AGU, but it's in context here. There's going to be a picture of my mum that she didn't know about, but my mum's here in the audience too. So I became an AGU fellow, as Harry said, in 2007. He said at the beginning of the intro. That might just sound, oh yeah, she became a fellow. Well, you know what? There were 6 women in a group of 63 men or something, and this is kind of a nuts statistic. We need to change this. So the reason for putting this up there was, I mean, we need to really change the way that we are awarding and promoting and everything to make things more balanced. And there's no reason why we can't have more women up there receiving honors, AGU honors, just like I did. So I think that's a really important kind of message to end on, and I'll leave it at that. How cold is the lake? So it's just right around freezing because the water's actually liquid. So, yeah.
Why doesn't it freeze?
Why doesn't it freeze? Because it's underneath a huge amount of ice, and it's actually okay, we'll take a step back. So Antarctica is sitting on top of a continent. So underneath you have geothermal heat coming up, and so a lot of it is actually melting on the bottom. But it's also there's a huge weight of ice above it, and that's also helping to melt it there. I just remembered that I was supposed to repeat the question. I was asked why.
You can repeat the question.
Okay. Oh, I did.
What is the salinity of the water in the lake?
So we actually don't know that yet. Oh, what is the salinity of the water in the lake? What is the salinity of the water in the lake? Well, we've only just sampled the lake, so we don't actually know. But we think that it's fresh water. And so once we have taken them out, literally these data have just been collected. So the results and everything are forthcoming.
That's exciting.
It's meant to be fresh water. That's what we're thinking. Yes, so this question is about the ice dynamics and the activity and why the lake drains and fills and why there's a sort of quiescent period in the middle. So that's a keen eye based on one of the time series that I showed, one of the only graphs. And basically what's happening is the water is receiving, so it's this one, I think, is that you were talking about. The water is actually coming from a catchment upstream, very small amounts over a large area, which ends up pooling in these subglacial depressions, and the subglacial water level rises to a point that it can't stay there anymore, and yeah, there's a seal that breaches and the water floods. So that's sort of what's depicted in this one right here, a little bit. But yeah, that's essentially what's going on. How can we get more women in the sciences? Well, so when I was at AGU last and speaking in December, my message to the women in the room was to encourage them to put themselves up for talks. Like, don't say they'll do posters, like actually nominate themselves to give talks. And we have to also be thinking about women for awards, and we need to be mindful of that. But you mean from the beginning in terms of schools and things?
Whatever it takes.
I mean, I don't know. I mean, just encouragement and strong role models and that kind of thing. With that in mind, my daughter has a question for me. The question from my daughter, Millie, was, if I want to promote women in science, why did I not name the lake after myself? Funny story is, actually, my colleague Ted Scambos, he called the lake, the first one that I found, this beautiful one here, Engelhart. We called it Engelhart. He calls it Lake Helen, and he sends me files still to this day, images over this lake, and his acronym for the lake is LH, Lake Helen. Here's a whole file for Lake Helen. So this lake could have been Lake Helen, but then what would the other ones have been called? I could have named them after you guys, but there's only 14 lakes. So we decided to name them for, one thing I know is that these, all the ice streams got renamed. They used to be called ice streams A, B, C, D, E, and F. Very boring. And they got renamed when Ian Willans passed away. Ice Stream B became Willans Ice Stream. But some of the other lakes got named after people that were still alive, and they found that a bit creepy. Like, the people that were still alive didn't like the fact that they had things named after them. Generally, you don't have something named after you until afterwards. So, yeah. So Doug McHale has an ice stream named after him, and Bob Binshadler has an ice stream named after him, but they don't like using those names. They call them by the old names.
So it's up to you to name something after your mother.
Yeah.
In the long run.
Yes, so all of the water under Antarctica is essentially meltwater that's come from the base of the ice. So it's being formed from this geothermal heat flux underneath, and also this frictional melting and pressure melting. So all these things act together it's a very small amount of water, but Antarctica's large, so a small amount over a large area, it pools into these catchments, and that's where the water's coming from. Yes. and that water hasn't seen the surface for a long time. So it's all water that's melted off the base of the ice sheet. So yes, it's old. Sorry, I should have repeated the question. Is the water old? I thought you said cold originally, but you said old. So the water is old because, and the properties will differ from current, yes. But they are going to also try and find out where the water came from too. So the origin of the water in the two different lakes. They want to compare and contrast. And now we've got two samples from two, so the water for this lake comes from here, and the water from this lake comes from here. So they're actually coming from two different sources of the ice sheet, so we can compare and contrast conditions in the water and also the sediment. So does the action of bringing the core up from the sediment, does that perturb the water column? Well, I mean, they do it as carefully as they can, but there's only so much you can do. Yeah, it will do. Yeah, so the question was about so I think you said I actually didn't remember which specific planets you said, but moons of, oh, I didn't hear. Okay, the moons of, okay. So, and whether the lakes that you see there would have similar properties, and should we think about sending satellites to those? Well, that's a whole, I mean, but I don't know. I mean, we don't know much about those ice fields. There is a whole new mission that's being started right now to go to Europa, and that's one of the goals of that project. Yes, I believe there is somebody on the project. Oh, is there anybody doing DNA on the organisms that are coming up from the sediment? And I believe that is what Tristy Vic Majors, who sent me a couple of these figures, is doing. I don't know exactly who's doing what in terms of the analysis, because there's multiple people and multiple postdocs and students involved, but there is somebody looking at DNA.
So I hope we can have you or someone in your group back to fill us in on what the fruit that's born from all of these wonderful studies. And I think it's just been such a privilege to hear about this leading edge of science. And I want to thank Helen again and thank all of you guys for coming.